Certificates are everywhere. Every time two servers talk to each other over a network, certificates are what make sure that communication is encrypted and that no one in the middle can intercept or tamper with it. We are talking protection against sniffing, against man-in-the-middle attacks, the real stuff. But here's the thing, the moment you start signing a certificate, you end up with a bunch of files, and if you are a DevOps engineer, a sysadmin, or a security admin, you need to know exactly what each one of these files is, what it does, and more importantly, which one you need to be careful with. I'm looking at your .k file. That one holds your private key, and if it leaks, your whole security model collapses. So yeah, we are going to take this seriously. Before we dive into each file, let's talk about something that trips up a lot of people, the encoding format. Because before asking what is this file, you should ask how is this file represented. And there are two formats you need to know. The first one is dir. Dir is a binary format, meaning it is not human readable and it is not suitable for copy pasting or image transfers. It uses ESNA.1 encoding, which is a strict and ambiguous way of representing data structure, and that ambiguity is exactly what it suits cryptography so well. You will commonly see it with extensions like .dir, .cir, or .crt. The second format is PEM. PEM takes the same binary data and encode it in base 64. So instead of a raw bytes, you get a letter and numbers. That make it image safe, text safe, and actually readable by human. Common extensions here are .pem, .key, and again .crt. And that brings me to something important. The extension doesn't always tell you the encoding. A .crt file can be either dir or pem. The extension tells you roughly what the file is for, not necessarily how it is encoded inside. So how do you actually know? Two ways. On Linux, you can use the file command on the file. If it says data, that's dir, binary format. If it says ASCII text, you are most likely looking at PEM. The other method is even simpler. Just open it in a text editor. If you see a header like this, that's PEM. If you see nonsense garbled characters, that's dir. Now, one last thing before we move on. You are going to encounter a file with the actual extension .pem, and when you do, that extension is being explicit. It is telling you directly that the content inside is in PEM format. Keep that in mind because it will matter when we get to that section. Alright, now let's go onto the files themselves. The .key file. This is the one you really need to treat with care. This file holds your private key, and that means it should never be shared, never be sent over an insecure channel, and never be stored somewhere without proper access control. Why? Because whoever has this file can potentially sign other certificates or worse, impersonate your server. If an attacker gets their hand on your .key file, it is game over for that certificate. Like we said earlier, this file can be encoded in either dir or PEM format, but realistically what you are going to see in the wild is PEM, and most of the time it will be encrypted with a password for an extra layer of protection. So even if someone manages to get the file, they still can't use it without passphrase. Now, if you want to inspect the content of a .key file that's in PEM format, you can use this command, and if the file happens to be in dir format instead, you just add the inform dir flag, and when you look at the output, you will see exactly what make up a private key. Things like the modulus, the public exponent, the private exponent, the prime numbers. These are the raw mathematical components that make asymmetric cryptography works. You don't need to memorize what each one does, but seeing them helps you understand that this is not just some random blob of data. There is a real math in there, and that math is what makes your encryption strong. So remember, treat the .key file like a password. Actually, treat it like something more important than a password. Next up is the .cnf file, and this one is a bit different from the others because it is not a cryptographic file. It doesn't hold any keys or certificates. It's just a configuration file, plain text that tells OpenSSL how to generate your keys and certificates. Think of it as a recipe. Before you start baking, you write down your ingredients and instructions, and that's exactly what the .cnf file is for OpenSSL. To take a look at one, you just use the cat command. Now, technically, when you are making a certificate request, you can just pass everything as a command line parameters directly to OpenSSL, something like this. But the moment you need to configure a lot of parameters, extensions, alternative names, key usage, constraints, that command line gets out of hand really fast. That's when you put everything into a .cnf file and just pass it to the tool instead. Much cleaner, much easier to reuse. And the file looks something like what you see here. One important thing to keep in mind, a .cnf file is not one size fits all. The parameters inside change depending on what you are trying to achieve. A config file for a root CA looks very different from a config file for a server certificate. The CA config will have CA true, it will have sign-in permissions, while the server config will have CA false, domain names in alt names section, and server authentication flags. Same format, very different content. The .csr file certificate sign-in request, and just like the .key file, this one can also be encoded in either dir or PEM format, though again you will mostly encounter it in PEM in practice. As the name says, this file is essentially a request. You are saying to the certificate authority, hey, I want a certificate. Here is my information, here is my public key, please sign it. So you package all of that into a .csr and you send it over to the CA. Now, if you look at the content, you will notice it has less information than a full certificate. That makes sense. At this age, the CA hasn't signed anything yet, so there is no issuer information, no serial number, no validity dates. What do you have is your identity information, country, organization, common name, your public key, and a signature made with your own private key to prove that you actually own that key. To inspect a .csr, you can use this, and for dir format, you can use this. Once you send this to the CA and they verify your identity and sign it, that .csr becomes .crt file, a complete trusted certificate, and that's exactly what we are going to look at next. The .crt file is the final product. This is what all the previous steps were building towards. Unlike the .key file which you got with your life, this one is meant to be public. It gets sent to every client that connects to your server. That's clearly how TLS works. The server presents the certificate so the client can verify who it is talking to and establish an encrypted connection. And you can see that compared to the .csr, this file has a lot more information in it because now the CA has done its job and signed it. So on top of everything that was already in the .csr, you now get a serial number, a unique identifier the CA assigns to this certificate so it can track, evoke it if needed, a signature algorithm telling you exactly how the CA signed it, an issuer field, this is new, this is who signed the certificate. In our example, that's let's encrypt. Before, in this .csr, there was no issuer because nobody had signed it yet. And the validity date, and not before and not after defining exactly how long this certificate is trusted. After that date, it is expired and clients will reject it. To inspect a .crt you can use, for dir format you can use this. Now the .pem file, and this one is where people get confused the most, so pay attention. Earlier we talked about PEM as an encoding format, base64, human readable with headers and footers, but now we are talking about .pem as an actual file extension, and that's difference matter. When you see a file explicitly named with the .pem extension, it is telling you upfront the content inside is in PEM format. No guessing needed, no opening it in a text editor to check. The extension itself is the confirmation. But here's what makes .pem file special. Unlike .k or .crt, which each hold one specific thing, a .pem file can hold multiple types of content, and you can tell what's inside just by reading the header. For example, a private key looks like this, a certificate request looks like this, and a certificate looks like this. It doesn't stop there. You can also have encrypted private key, DSA key, elliptic curve keys. The header always tells you exactly what you are looking at. The template is always the same pattern as you can see here. So a .pem file is really just a flexibility container. It can be a key, a certificate request, or even multiple things concatenated together in the same file. The header is your guide. And finally, the .pfx file, also known as .p12. They are the same thing, just different names. This one is special because unlike all the other files we have been so far, the .pfx is not a single purpose file. It is a bundle, a container that packages everything together in one place. Your private key, your certificates, and the certificate chain all the way up to the CA. Everything in one file. And as we talked about earlier, the outer wrapper of a .pfx is encoded in their binary format, PKCS12 to be precise. So if you try to open it in a text editor, you will get exactly that garbage output we showed you earlier. That's expected. But inside that binary container, the individual pieces, the certificate and private key are stored as PEM encoded objects wrapped in what's called bags. And each bag has attributes that describe what is inside, like a friendly name, so you can identify which certificate is which, and a local key ID that links the certificate to its corresponding private key. To inspect the content of a .pfx file, you can use this command. But because it bundles the private key inside, remember that we said about the .key file. Treat the .pfx with the same level of cautious. Actually, in some ways, it is even more sensitive because it has everything in one place, always protected with a strong password. Now let's talk about something that isn't enforced by any tool or standards, but will save you a lot of headache in real life, naming conventions, because here's the reality. OpenSSL doesn't care what you name your file. You could name your private key banana.txt and it would still work. But when you are managing multiple certificates across multiple servers, bad naming will absolutely come back to bite you. The most common convention you will see is using the extension to tell you the type and the name to tell you the role, something like this. Clean, simple, and at a glance you know exactly what each file is and who it belongs to. Some teams go to other direction and use .pem for everything, leaning onto the fact that PEM is just encoding format and letting the file name carry all the meaning. This approach is actually very common in tools like Kubernetes, Terraform, and Vault, where everything tends to be .pem and the file name is what differentiates them. And then some tools get even more explicit, especially when you are dealing with cluster or multiple nodes. Here you know not just the type but exactly which node that certificates belong to. Very useful when you are rotating certificate on a cluster and you don't want to mix anything up. The convention you choose doesn't matter as much as being consistent. Pick one style, stick with it across your whole infrastructure and document it, because 6 months from now, when you are troubleshooting an expired certificate at 2 a.m., the last thing you want to be doing is figuring out which .pem file is the key and which one is the certificate. Now, before we close out, I want to show you two files that nobody talks about, but you will definitely run into if you are running your own certificate authority. Consider this as a bonus. The first one is the serial file, and it is probably the simplest file in this whole video. It is just a file that contains a single hexadecimal number. That's it. But that number is important. Every time you see a signs a new certificate, it reads this file, assigns that number as the certificate serial number, and then increments it for the next one. Remember the serial number field we saw in the .crt file? This is where that comes from. So if you open it and see something like this, that means the next certificate your CA size will get serial number 04, and after that the file will update it to 05, and so on. It is a simple counter, but it matters because serial numbers are how the CA tags and evoke certificates. If two certificates share the same serial number from the same CA, that's problem. This file makes sure that never happens. The second file is Index.txt, and this one is essential the database of your certificate authority. Every certificate your CA has ever signed gets a record in this file. Think of it as a logbook. Each line in the file represents one certificate, and it has several columns separated by tabs. Let me walk you through each one. The first one is the status. It is a single letter, V, meaning the certificate is valid, R meaning has been revoked, and E means it expired. At a glance, you can see the head of every certificate your CA has issued. The second column is the expiry date, the date and time when the certificate expired in this format. This is the same not after date you saw in the .crt file. The third column is the revocation date, and this one is only popular if the certificate has been revoked. If the certificate is still valid, this field is empty. If it was revoked, you will see the date and the reason it was revoked here. The fourth column is the serial number, the hexadecimal number we just talked about in serial file. This is how you can cross-reference a certificate in the index with its actually .crt file on disk. The fifth column is the file name, usually unknown in most setup, but it can point to the path of the certificate file. And the sixth column is the distinguished name, the full identity of the certificate, the subject field we saw earlier, country, organization, common name, all of it. So a line in index might look something like this. And if the certificate gets revoked, will look like this. Together, the serial file and the Index.txt are what turn OpenSSL from just a crypto tool into actually functioning certificate authority. Small files, but they carry a lot of responsibility. Now you know not just what these files are, but how they relate to each other and where this fits in the bigger picture. Next time you are setting up CA, configuring TLS, or just starting a directory full of cryptographic file extensions, you will know exactly what you are looking at. If you found this useful, drop a like and subscribe because we have a lot more content coming around certificates, PKA, and security in general on Asgard Tech. And if you have questions, drop them in the comments. I read every single one. See you in the next one. Bye bye.